The main portion of the crane, what's called the fixed tower, starts coming down. You can see it hit the Google building.
On April 27, 2019, a tower crane came crashing down in the middle of Seattle's busiest street, killing 4 people. The truth behind that fall wasn't about the weather. It was about decisions made long before the wind ever touched the steel. To understand how something so massive could fail so suddenly, you first need to know the machine itself. It was a Liebherr tower crane, built in Germany by one of the world's most respected engineering companies. Tower cranes like this are the backbone of every skyline you see today. This crane could lift up to 32 metric tons, around 70,000 pounds, with enough accuracy to place heavy steel beams within millimeters of their marks. Machines like this cost between $2 and $3 million, making them not only technical powerhouses, but also major financial assets on a project. But the complexity goes even deeper. A tower crane isn't a single piece of equipment, it's a modular system designed to grow with the building. Its mast is made of lattice sections, bolted and pinned together, each engineered to transfer massive compressive loads straight down to its foundation. The steel pins that lock these sections together are precision machine components. They aren't simple rods. They're heat-treated, load-rated, and designed to resist shear forces that can reach tens of thousands of pounds. The crane's long horizontal jib acts like an outstretched arm, distributing loads and counteracting forces using leverage. On the opposite side, huge concrete counterweights, sometimes weighing over 20 tons, provide balance. These counterweights are precisely calculated. Even a small miscalculation can shift the crane's center of gravity, creating enormous sideways stresses. When assembled correctly, all parts of the crane work together like an engineered ecosystem, capable of withstanding wind loads, dynamic loads from lifting, and constant cyclic stresses from daily operation. And that's the key. Tower cranes are engineered with safety factors built in. A properly erected crane can withstand wind speeds far beyond normal storms. Many are designed to endure 70 to 100 miles per hour gusts, depending on configuration. They can even weather vane, rotate freely in the wind to reduce stress when not in use. So if something this robust can collapse under a normal gust, then the danger didn't come from the wind. It came from the people working with the machine. That's where this story begins to twist. The crane wasn't lifting anything when it fell. It was being dismantled. And dismantling a tower crane is one of the most delicate and dangerous phases of its entire life cycle. While assembly is controlled and predictable, dismantling has additional risks. Gravity is working with you and against you at the same time. If one connection is undone too early, the entire structure may become unstable in a matter of seconds. A proper dismantling process follows a strict sequence. Certified workers climb the mast to remove bolts and pins from a single section at a time. They secure the slewing assembly with hydraulic jacks, attach a mobile crane to carry each removed section, and only when everything is locked, checked, and verified do they extract the pins. These pins are the backbone of the mast. Lose too many and the tower becomes a hollow shell supported only by friction and luck. But on that day in Seattle, something very different happened. High winds were forecast for the next day. The dismantling crew, an experienced group from Northwest Tower Crane Service, didn't want to be halfway through the process when weather rolled in. Construction schedules are notoriously tight. A delay of even one day can trigger cascading costs. Idle workers, postponed concrete pours, delayed subcontractors, equipment rental penalties. Under that pressure, the crew made a decision that would change everything. They removed far more pins than the manual allowed. Instead of removing pins only from the section they were actively working on, they removed pins from multiple sections ahead of time. Some of these sections were still bearing structural load. With those pins gone, the mast lost its redundancy. The connections that were supposed to resist thousands of pounds of shear force now relied on a fraction of their original strength. Engineers later said that in this condition, the crane had almost no lateral resistance left. A properly secured crane behaves like a rigid column. This one was more like a loose stack of steel frames held together by gravity. And then the gust arrived. At 3:30 p.m., a 48-mile-per-hour wind hit the site. Under normal conditions, a fully pinned crane would have simply rotated with the wind. But this crane couldn't rotate freely. The dismantling process had locked certain components in place. The jib acted like a giant sail, an enormous surface catching wind from the side. The remaining pins were never designed to hold the entire structure under that kind of lateral force alone. Witnesses described hearing a series of sharp cracks, like gunshots. Those cracks were the structural pins failing in shear. Once a few pins snapped, the load shifted violently to the remaining ones, and they failed in rapid succession. In engineering, this is called a progressive collapse, where one failure triggers another, accelerating in milliseconds. The top assembly, about 204 metric tons of steel, ripped free and began falling. The mast twisted, buckled, and then the whole structure collapsed into Mercer Street. 4 people lost their lives. 2 of them were iron workers on the crane, experienced professionals who trusted that the structure beneath them was secured according to procedure. The other 2 victims were people simply driving down the road, unaware that the machine towering above them had been fatally weakened hours earlier. And here's the question many people ask: how could skilled professionals take such a risk? The answer is something called the normalization of deviance. When teams perform the same complex task repeatedly, they sometimes discover small shortcuts that seem to save time. If nothing goes wrong the first or second time, the shortcut starts to feel safe. Over the years, habits form. Those habits become the real procedure, quietly drifting further from the official one. Until one day the conditions are just different enough, and the shortcut turns deadly. Investigators concluded that multiple companies contributed to the failure. Oversight systems failed to catch dangerous habits. Contractors failed to enforce written procedures. Safety audits didn't identify shortcuts that had become routine. And at the core of it all was the premature removal of critical pins. The fallout was staggering. Besides a tragic loss of life, the financial impact rippled through every part of the project. The crane, worth up to $3 million, was destroyed. The cleanup and structural repairs to the Google building and surrounding area ran into the tens of millions. Delays pushed the project's timeline back, adding millions more in indirect costs. Lawsuits from victims' families and involved parties eventually exceeded $100 million. All told, the total financial damage surpassed $200 million. But something did change. Washington State recognized a major gap in its regulations. Crane operators needed certification, but the crews assembling and dismantling cranes did not. Senate Bill 5693, passed in 2020, changed that. It required certified training for assembly and dismantling crews, mandated detailed safety plans, and strengthened oversight, directly inspired by lessons from this collapse.